Hello, chemistry students. So we're about to embark on chemistry unit 5.
This will be talking about the periodic trends and the ionic compounds.
So in our first lesson, we're going to focus on the periodic table trends. This is lesson 5.1. So the objectives would be to, first of all, identify the different blocks or groups of elements that we give names to on the periodic table.
And the second one is to describe trends and properties of atoms across each row, also known as periods, and down each group, known as families, actually. So the first definitions we want to talk about is the word period. It's also known as a row. This is the filling in electrons on the same energy level. So n equals 1, n equals 2, n equals 3. Those are your rows of the periodic table. And the second definition is a group or family. These are your columns. And they have the same pattern in outermost electrons. Some are named halogens, noble gases, and alkali metals. Good ways to understand what you mean by the same pattern in outermost electrons. If you remember back to the ground state electron configurations, they would all end in the same outermost electron configuration.
So it all end in S2.
Yeah.
And certainly every single thing in that column has an S2 that makes them a group or a family.
We'd be talking in that case actually about beryllium, magnesium, calcium, strontium, barium, and radium. All right, let's go on to some trends. Sorry, I was wrong. We're going into labeling. So on, you have a page right after your notes that looks very similar to this. You don't need to fill in with color. Just designate these in some way that you understand what they are. So the very first column we're going to talk about are the alkali metals.
Hey, let's just go through metal and non-metal before we
Let's do
start
that first, yeah. So we have metals and nonmetals and metalloids on the periodic table. The metals are all found to the left of the stair-step line. It's called a stair-step line because it looks like a black set of stairs right there. Next, we have nonmetals. They are found to the right. And then lastly, along the stair steps, we have what is known as a metalloid, and they're called metalloids because they share
some properties with both metals and nonmetals.
Exactly.
So your elements like silicon and arsenic and gallium and some of those. The one exception to that is this little guy right here, hydrogen, which is definitely way on the left. And for some other reasons, they always stack it in here with these group 1 metals. But hydrogen is most definitely a non-metal element, so its properties are going to be more along the lines of these elements over here, even though it's over here with the metals.
Yep.
And you can see, just looking, the majority of the elements on the periodic table are metals, not non-metals.
Okay. So now let's go back to labeling these columns. The first column we're going to talk about are alkali metals. It is the first column, labeled 1A or just 1.
Notice I skipped hydrogen.
Yes, you did. The second one is the alkali earth metals. That's the column right next to it, column 2.
So we're going to go the blue on these guys. You can color them anything you want.
Yes. Next is transition metals. That's actually the D block plus part of the underneath the stair step. The ones under the stair step are sometimes called other metals or poor metals. But the D block are definitely the transition metals. Some people, like I say, do consider the next thing here to also be transition. So, I mean, it all depends. For us, we're going to deal with them all as transition metals. Metalloids are the next thing we're going to talk about.
Go yellow.
So metalloids, those are the ones that are along the stair step. Right there. There are exceptions to the metalloids, or the ones that are along it, but we'll talk about those more in class or as they come up. Next, we have halogens. Those are the ones that are in row 7 or column 17. These are your highly reactive, normally gases, but are also liquids and solid. Highly reactive and dangerous because they want to gain one more electron. And the last one that's really important is the noble gases.
What color? I didn't use purple yet.
So the noble gases are the next rather important group. There's also the lanthanoid and actinide series, but they're not really large on our.
No, we'll color them in. That's these two rows, and sometimes they're also referred to as the inner transition metals
Or rare earth metals.
or rare earth metals. So they've got a lot of names.
Okay. Right, let's go on to the next thing.
So we're going to look at three properties that atoms have that have strong periodic trends, which means that they kind of change in a trending fashion as we move across the periodic table or up and down it. And the first one is the atomic radii or atomic radius. And the book definition is this is 1/2 the distance between the centers of a homonuclear diatomic molecule. So what that means in kind of normal, if we have a diatomic molecule,
2 atoms.
which is 2 atoms of the same thing that are bonded, and we measure the distance between their centers, 1/2 that distance, which would be, this much, is the atomic radius. So since atoms, the electron cloud is not like a hard shell, you can't actually measure from the nucleus to, the electron cloud, sort of a fuzzy. So it's kind of hard to determine the exact size. But we can measure the distance between the two nuclei, and then half that, and that's a good, an estimate of the size of an atom, or kind of relative size of atoms. So the second property is electronegativity, and electronegativity is measurement of how strongly an atom wants to hold on to shared electrons when it's in a chemical bond. You can think of it as a hunger for electrons or a pull for electrons. So it's a number between 0 is no electronegativity, and I think 4 is the highest. And it's a kind of an arbitrary scale that scientists have set up. But so the higher the number, the more electronegative, the more pull the atom has for electrons. And the third one is ionization energy. So if you were to take and measure how much energy you'd need to apply to knock off or to pull off the outermost electron, the most loosely held onto electron from a gaseous atom, that is the ionization energy. So we're going to look at how these three properties vary both across and up and down on the periodic table on the next slide.
So the first trend we want to put on this periodic table is the atomic radii.
And by the way, you're going to want to turn to page 15 in your packet. You don't want to have to draw that.
Yep. So atomic radii is the trend that it follows as you move down the periodic table, and from right to left across, you increase in the atomic radii. The reason this happens is there's an effect called shielding. You should write this word down. Shielding is when the electrons shield or block the effect of the nucleus on the other electrons. So that's why they would grow larger as you move down and across, because then there are more electrons as you move down and across, so the ability of the nucleus to hold on to those outermost electrons becomes weaker. The next two...
So that to me is just, like, I would think, and it runs a little counterintuitive, because I want to, like, you'd think, like, the atoms get larger as we go this way, but yet, in size, but yet if we're counting particles and, like, electrons, they get bigger as we go this way. So I guess that's the thing that Mr. Hunter was talking about with that shielding. As you move across the period, you're not really adding any more layers of electrons. You're still filling in the same energy level, but yet you're adding a lot more protons. You have, over here, 36 protons. Here, you only had 19 protons, so you have a lot more positive pulling on those same electrons. So these atoms are much smaller than these, which is, again, it's not,
That's
doesn't
weird
seem to
to
make
think
sense.
about,
It's weird, but so make sure you kind of have that down. So we increase going down, and then we increase from right to left.
All right, the next two trends follow the same trend. It's ionization energy and electronegativity. That increases as you go from the bottom up and then from the left to right. Again, shielding would be your explanation for this. As you move across the periodic table, you're adding more electrons, so they're not feeling as much pull from the nucleus, so it's said that backwards, sorry. They're able to attract more electrons as you move across the periodic table and up, so they can pull them off of their neighboring electron or their neighboring atoms if they have a lower electronegativity. And the same goes for ionization energy. They don't want to let go of those electrons as easily as you move up and across, because the nucleus can hold on to those electrons more readily.
Now, the one exception I'm going to kind of draw a line down through here is our noble gases. Now, they do have an ionization energy. You can knock an electron off. They have a very high ionization energy. And in fact, following the trend, we would know that helium has the highest of all ionization energies for knocking off that first electron. But the electronegativity stopped here. These noble gases, the ones in group 18, have no electronegativity.
Yes.
So we might want to note that this whole group 18 here, they have no electronegativity. That says no electronegativity, believe it or not.
Okay.
So what the most electronegative element would then be fluorine,
And the least is
and
francium.
the least would be francium down here. By the way, Mr. Hunter, what would be the largest atom? on the
Also
periodic
francium
table?
in this case.
Francium.
And the smallest would be, helium.
Helium.
Okay.
All right.
So here you see a kind of a pictorial representation of the atom's atomic number and the ionization energy required. As you can see, it follows a trend of going up, then down, up, down, up, down. And you kind of see that pattern. That pattern you have to recognize, but what that means is each of these colors that you see is actually a different energy level on the periodic table. Hence, there's more and more bars per row. So as you move across that row, it's telling you it takes more energy to ionize these atoms and make them into ions.
So the black is hydrogen and helium.
And the next
This would
one's
be
at row
lithium
2.
through neon.
Yep.
Okay.
And notice there are exceptions, but we don't expect you to know those exceptions.
There are some little dips. There's some like stable configurations in between, but the general trend is as you move, this would be the fourth period from potassium over to krypton. And you can see the general trend is it goes up, 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 and krypton has the highest ionization energy of anything.
Okay, let's take a look at the next trend. So here's another visual representation of atomic number with the atomic radius. Again, you can see it has this same type of pattern, except for now it's reversed. It starts tall or larger, and then it goes down, goes down, goes down. Again, there are exceptions to this. We're not going to learn those exceptions at this level. But it's just good to understand the pattern, and that every energy level follows the same pattern. As you move from left to right, you get smaller. And as you move from the bottom to the top, they get smaller as well. So this is just a nice little representation of this. So here are your PVQs. Do your best to answer what electronegativity is and to name and describe another property of atoms that is a periodic trend besides electronegativity. And we'll talk about it tomorrow in class.
Okay.
Have fun.
See you then.